The section here on trapezoidal approximations actually comes from 5.5, but notice how closely it resembles our work with rectangle approximations. I like to teach them together. So if we are trying to approximate the area under the curve, probably because we're trying to find distance traveled by finding the area under a velocity curve, then we can use rectangles. We know we're only going to get an approximation. If we want our approximation to be better, if we want to increase our accuracy, we have two options. We can either use more rectangles and more rectangles, or we could find some shape that's better than a rectangle. Find some shape that matches the curve more closely. And it turns out for most functions, for most curves you'd want to find the area under, a trapezoid is going to fit more closely than a rectangle will. And the computation isn't too much more complicated, finding the area of a trapezoid versus finding the area of a rectangle. So remember, you know how to find the area of a trapezoid. You probably did this in geometry. But in geometry, most of your trapezoids sat with their parallel sides horizontal. So you found the average of the two parallel sides, that's base 1 plus base 2 divided by 2, and multiplied by the height, which is the distance between the parallel sides. Most of the time in calculus, all of the time that we're going to use a trapezoid to approximate an area under a curve, our trapezoids are going to be standing up. Their two parallel sides are going to be vertical. So we usually think of this as a height. I'm going to call this height 1 and height 2. We're going to find the average of the two heights and multiply by the distance between those two parallel vertical sides, which you might think of as the width of the rectangle. I'm going to call it base. So the average of the heights multiplied by the base to find the area of a trapezoid. So just notice what this looks like. In one of the earlier videos, we were trying to find the area under this velocity curve. We said we could have rectangles touch. We were going to have 4 rectangles. We said we could have them touch at the top left corner. And so this is the picture we drew. Notice, since this function is increasing, every one of our rectangles leaves some space between the rectangle and the graph. We said, oh, well, we could have picked to have our rectangle start at the other corner, and we would have drawn this picture. Our rectangles could touch at the top right corner. Right, so notice the difference. If I have a trapezoid, I actually have it's not a rectangle anymore, but it's like it would be a rectangle that touches at both the top right and the top left. So I'm going to take the top right corner, that's the top left corner, and the top right corner on the interval 0 to 1, I'm going to have these connect. And when I draw this, I have a trapezoid. Here's my rectangle. It's not a rectangle, it's a trapezoid that covers from 1 to 2. I'm going to connect my top right corner and my top left corner. Here's my trapezoid that covers from 2 to 3. And you can see in this picture, it's not a very complicated graph, but it happens that you can see the difference between the area of the trapezoid and the area under that curve in that section. There's so much less error. So the trapezoidal approximation is the 4th kind of approximation you'll be expected to perform on the AP test. Here's how that might look on the AP test. Car A has a positive velocity as it travels on a straight road. Velocity is recorded and given here in this table for some time values on the interval from 0 to 10. Use data from the table to approximate the distance traveled using a trapezoidal sum with 4 subintervals. Show the computation that lead to your answer and indicate units of measure. So notice they're not going to mess with you on the AP test. They're very clear about what interval you should cover, 0 to 10, and that we should use 4 subintervals. That means 4 trapezoids. So the first trapezoid is going to cover from 0 to 2, the second trapezoid from 2 to 5, the third from 5 to 7, and the fourth trapezoid from 7 to 10. So I'm going to write this expression, average of the heights times the base, for each of 4 trapezoids. So the average of the heights, the 2 heights I'm going to use for my first trapezoid are the height of the curve at time 0, which is 0, and the height of the curve at time 2, which is 9. If I were using LRAM, I would have used the 0. If I were using RRAM, I would have used the 9. For the trapezoid, I use them both, but I have to divide by 2. I take the average. So I'm going to write 0 plus 9 over 2, and I'm going to multiply that by the base. That's the distance across this trapezoid. Well, this trapezoid covered from 0 to 2. That's a distance of 2. That was my first trapezoid. I have 3 more to go. My second trapezoid, the average of the heights, that's going to be 9 plus 36 over 2. The over 2 is from taking the average. I'm going to multiply by the width of this trapezoid. This trapezoid covered from 2 to 5. It has a width of 3. My third trapezoid, my heights are 36 and 61. 61 over 2. And I'm going to multiply by the width of that trapezoid. That trapezoid covered from 5 to 7, which is a distance of 2, a time interval width of 2. And my last trapezoid, my heights will be 61 and 115. I need their average. I'm going to multiply by the distance across that time interval, which is 3 seconds. So when I simplify that, I get 9 plus 67.5 plus 97 plus 264, which gives me 437.5. Notice if this were the actual free response section, you'd have no obligation to simplify any further than that. Feel free to leave your answer like that. One other thing we've been asked for is for units. So notice that for every one of these trapezoids, I computed area. That was the average of the heights times the base. Notice the heights were all measured, they were all velocity values, and they were measured in feet per second. So the average of 2 height values is also measured in feet per second. And then every one of those averages was multiplied by a base, a distance across a time interval, which is measured in seconds. So these were all measured in feet per second times seconds, which makes feet, which means I added feet plus feet plus feet plus feet, and my answer is 437.5 feet. Here's a problem from an AP test. A scientist measures the depth of a river at one place across the river. The river's 24 feet wide. That's why my distance from river's edge goes from 0 to 24 feet. I'm going to start on one bank and give measurements as I move all the way across toward the other bank. And the measurements are taken straight line and perpendicular to the edge of the river, and here's the data. So let's draw a picture just to make sure we understand what's going on. There's a river, and there's one place on the river, let's call it Picnic Point, and I'm going to imagine I can walk across this red line, and I have some kind of fancy scientific equipment that can tell me how deep the water is at, some point that I'm at across this red line. And I'm going to try to use that to figure out, if I were to slice the river right there, what would the area of the face of that slice be? And what I find out is that when the scientist comes along and measures that, she finds out that right at that point, the water is 0 feet deep, and then 7, and then 8, and then 2 feet, and then 0. So really, I was about to draw in lines. We actually don't know what happens in between those dots, but you can imagine some curve connecting those points, but we'd like to find the area between the red line and the blue curve. And since we don't know a formula for that curve, we won't even be able to use all our new techniques from chapter 5 on it. The best we're going to be able to do is make an approximation. So here we've specifically been asked to make a trapezoid approximation, which means you're going to be able to imagine connecting these points with trapezoids. Notice I didn't remember what the input values were, so I haven't marked them. But it's essentially the areas of those 1, 2, 3, 4 trapezoids that we're going to add together. So my calculations here, I've been specifically asked to use the 4 subintervals indicated by the data. So don't try to make up like the 0 to 3 and the 3 to 14, time intervals. They've given you time intervals in the table. These are the ones you should use. So we're going to have 4 trapezoids. The first one covers the distance across the top of the river from 0 to 8, then from 8 to 14, from 14 to 22, and 22 to 24. So I'm going to find the average of the heights of those trapezoids and multiply by the distance across, essentially the distance across the river that trapezoid covers. So I'm going to take my average of 0 plus 7 and multiply by the difference between 0 and 8 is 8. My second trapezoid, my 2 heights are 7 and 8, so I will take their average. To be very clear, that was a 0, right? And I'm going to multiply by the distance across the second trapezoid. The second trapezoid covers from location 8 to location 14. That's a distance of 6. My third trapezoid has heights of 8 and 2. We'll take their average and multiply by the distance across that trapezoid. It goes from 14 to 22, which is a distance of 8. My fourth trapezoid, the 2 heights are 2 and 0, which makes it a triangle, not a trapezoid, but that's okay, this still works. And I'm going to take their average and I'm going to multiply by the distance across that trapezoid from 22 to 24 is a distance change of 2. Okay, you have no obligation on the AP test to simplify further than that. Well, it turns out Part B asks you to use your answer from Part A. So you might want to simplify it, but you have no obligation to simplify that in order to get points for this problem. So I have simplified it, and we definitely still have one more job to do, which is to tell the units. So this makes 115, and I'm going to have to think about units. So there's one way to think about it. We've been asked to find the area of the cross-section. Well, what units do we think we would use for area? They're distance times distance units, and the only distances in this problem are feet, so it's going to be feet squared. We can check this another way. Every one of those areas of a trapezoid, they came from finding the average of the height, whatever height meant. Well, height is the depth of the water in that section, which is measured in feet. And we were multiplying by the distance across the top of the river, or the distance across that red line segment that I had drawn, which is also measured in feet. So feet times feet, make feet squared, and notice every one of the 4 trapezoids would have those same units. So our units, feet squared, or square feet.